All right, so we haven't had these live product showdowns in a while, so it's my pleasure to be here. As Tamar said, I'm a solution architect here at Firebolt, working with customers on the field, implementing solutions on top of our technology. And so today I want to share some progress that we've been making in the last couple of months with our technology, with some new features. We're going to talk about like Firebolt overall, what it is, what kind of solutions we want to deliver on top of it, and we want to show you a few cool demos. So first off, I want to start with a customer of ours. So I want to go kind of to the end state of what we want to do with Firebolt. And I want to show you a solution that this customer is using. They're called SimilarWeb. I guess many of you have heard about this company. In essence, they are a huge data collector. They index or crawl the web. They kind of analyze or synthesize this data, and they produce data models, which they expose to their end users or customers through their UI and various other channels. So SimilarWeb deals with a lot of data. You can see some of this information on their website, like 2 terabytes analyzed per day. Historical data is quite large. I mean, we're dealing with really kind of going into petabyte scale. And for their solutions, they really expect the data insights to be delivered snappy, right, performantly. Let's go and take a look into one of the modules that they're running on Firebolt. So this is called the ranking distribution. And in a while, I'll show you also the Firebolt side of it. But first, I want to focus on the UI, right? So this is a data application, and what it allows you as an end user, it allows you to analyze websites according to their ranking on Google. And this breaks it down even more, kind of according to keywords, according to trends, different time periods you want to analyze, and even gives you a comparison to your competition, right? So in this particular example, we're looking at adidas.com. We're looking at January data for United States, right? So if I want to focus on like the UK market and I refresh this page, you see that the kind of the response of the page is really performant, really fast. And so every refresh that I'm doing, every change of these parameters or filters is a query or a set of queries to Firebolt. We don't do any results set caching here. All of this is kind of live SQL running on top of Firebolt, crunching the data and giving it back to the UI. So you can see kind of really fast performance, and this is what we pride ourselves on and what we want to achieve with our customers, right? So let's go a bit further. We analyze adidas.com against its competition, right? So now it gets a bit more heavier or intensive on the data side. Now we're kind of going through a number of different websites, collecting the keywords and comparing them, showing them here on this UI. You can see again, quite snappy performance. Even if I go and change the filters here, right, everything is coming back within a second or two. I can do further things. I can kind of do some keyword search here. Let's try to do this on the shoes, and let's buy this. So I'm again filtering this kind of heavy queries, but now focusing on specific keywords that I want to analyze. So you see the performance going on really huge volumes of data, being really snappy and giving you kind of live queries. Nothing is cached from like the results perspective. Every query that's running here is live, being crunched in real time and getting back to the UI. So this is the end state we want to achieve, right? Now let's talk about like what are the challenges to come here. I've shown you the kind of SimilarWeb UI, their solution. In essence, it's a data app, right? A data application. And we, in the field, working with customers, we see kind of the rise of this evolution of BI going to more embedded analytics, going to data applications, right? So really applications that are heavy on the data side, which are heavy on the interaction between the end user and the actual data, and which really rely on kind of high performance of the underlying data store to be able to kind of engage the user, right? You don't want the user to wait for like 10, 15 seconds, wasting their time, right, and their attention. You really want them engaged. Give them insights as fast as you can. And so today we see a number of challenges in kind of getting to this performance, right? Most data app solutions, they come to a performance snag or kind of low performing situations where they want to, or they need to actually compromise, right, to solve this problem. The technology that they're using today forces them to either pre-aggregate their data, right, in which case they're kind of losing the raw granularity, the kind of the raw data, right? The lowest level of granularity. And this means, of course, they cannot provide deeper insights. They can only do, for example, month level or quarter level reporting, right? The other compromise is kind of to cut off the historical data. So you cannot do an analysis over more than 6 months of your data set, for example. Of course, the kind of the worst thing to do, which some of the kind of technologies force you to do, is put more money into solving this problem, right? There's this meme here, which kind of, I think it encompasses the situation very well, which, throwing money at the problem can only get you so far. And so we at Firebolt, we want to take a different approach to solving this problem. Firebolt, kind of our main premise is we want to be a cloud data warehouse for data applications. And really, we want to focus on performance and cost efficiency. So every query that runs on Firebolt, we have this kind of obsession that it needs to be sub-second, right? Internally, we really love seeing our customers achieving great performance over large data sets, right? Or they can be smaller data sets with complex queries, right? The kind of the end result is the same. We want to have sub-second experiences that power your data applications. Of course, we want to do this cost efficiently. So in the next slides, when I talk about different engines and so on, you'll see kind of the different approaches that we use to be cost efficient and to be predictable in this cost. We want to be developer focused. We are a cloud data warehouse. We're a software as a service, so fully managed. We really want developers to be focused on solving the problems, the data challenges, and not really focused on the infrastructure and how to achieve this, right? So with a few clicks of a button, you get a database provisioned, you get your engine set up, you can fully work with Firebolt and manage it through REST APIs and SQL. So basically, you can do everything from kind of the skill sets that you already have. And finally, we're built on AWS, meaning that we're using kind of a modern architecture approach. We're making use of AWS resources. I'm going to show you in a second how this looks like. So the architecture of Firebolt is presented here. It's kind of a high-level view, but essentially we are dealing with kind of multiple layers of the architecture, right? So at the bottom layer here, we have storage. We're using AWS S3 as our cold store. And the source for this, for all data coming into Firebolt, is your data lake, right? So this is your S3, where you have your data in various formats. It can be Parquet, Avro, CSV, whatever type of format you have, and you ingest this data through a Firebolt engine into our storage, right? So what happens is during this ingestion process, we actually transform your kind of original data format into something we call F3, triple F. During this process, we sort the data, we compress it, we index it. I'm going to talk about indexes in a moment. And then this data is actually served to the Firebolt engines, right? So you can see this kind of middle layer here, the compute layer, is comprised of a set of engines. You can have one or many running at the same time. And each of them is basically an instance, a compute instance within AWS, completely isolated one from each other and serving your data to the end users, right? So you can have, what this allows you to do is kind of decouple your use cases because the compute and storage is decoupled. You can have multiple engines serving multiple different use cases. For example, internal BI use case can go through a specific engine here called the dashboards engine, for example. You can serve your customer-facing workloads through a separate engine, which is then isolated and dedicated only for this use case, and so on, right? Dev engines, ELT engines, whatever you want to. Then on top, we have kind of the services which enable you to interact with Firebolt. So this can be our UI, for which you do the administration, for which you run queries, etc. Security, of course, and then on top of this, different channels or different protocols of talking to Firebolt. It can be REST APIs, it can be JDBC. There's wrappers like SDKs for various programming languages. We'll get to that in a second. So this is our architecture, right? I talked about engines a bit, the compute power, right? And here we really want you to find kind of the best fit for your workload. We are going with a granular selection of engines. So there's basically a couple of families of engines, ones that are optimized for compute. We have engines optimized for storage, for memory, or a balanced family. And basically within each of those, you can also choose very specific engine configurations, right? So the point here is find the best fit for your workload. Don't go, over the board. Don't go, don't spend too much if you don't need to. You can find really like optimum compute for your use case. Once you choose your compute, you can also choose the engine scale, right? That's the number of nodes that each engine will have, right? You can go from 1 node to a 128 node engine. And really, this is kind of how you scale out, how you support parallelism, and how you support, concurrency and things like that. Again, you can go really stepwise from 1, 2, 3, 4, etc. nodes, and not really have huge jumps between, low, medium, high in terms of the node count. There's various other options. We can discuss those in the demo. All right, the secret sauce, like what makes Firebolt efficient? Apart from the kind of query execution and the actual kind of engines and the infrastructure, we pride ourselves with different indexes. And really, there's kind of 3 index types that we usually discuss. There's more to come on this. But today, what you can do is you can kind of implement or create different index types to support different query patterns. And you'll see in the demo that this is really something that's simple to do. We want this to be kind of developer focused, so create it once and almost forget about it. The solution itself or Firebolt itself will maintain a lot of this for you. So 3 different index types. First, the sparse index, or what we call the primary index, is you can view this almost as your kind of sort key for the table, right? So each Firebolt table can have a primary index, which sorts the data according to this 1 or more columns that are part of the index. So imagine you have like a date column. Your data, when it's being ingested into Firebolt, it's going to be sorted according to that date column. And then we're going to apply compression on top of that to even further compress your data set. We are a columnar data store. And so sparse indexing can really help you here kind of index the ranges of data and get you only the data that you need, right? Firebolt here is very efficient in pruning. We are not talking about micro-partitioning or anything like that. We really are indexing on ranges of data, and this allows us to very efficiently fetch data from S3 and serve it to your use case or consumer. So this is the sparse index. Every table can have a sparse index. You can define columns which are part of it. Second 2 index types are more specific to your actual queries, right? The join index is essentially a hash table, the one that gets created during your normal join between, let's say, a fact and a dimension table. But this one is kept in memory, so in the RAM of the engine. And this means we save some time in actually creating this for each join. We can reuse what's already in the memory and kind of do very efficient lookups, very fast operations, and fetch data from memory, serve it from there. So join indexes really expedite your kind of star schema models. Wherever you have joins between different tables, usually fact to dimension, and where you can go kind of from n to 1, join indexes really help expedite this type of queries. And finally, we have the aggregating index, which is almost, you can view this as almost an automatically maintained rollup. So you have your base table with the raw data, and then 1 or more aggregating indexes on top of it, which kind of automatically roll up the data to the level of aggregation that you need. So again, imagine you have some sort of time series data. You want to kind of roll this up to hour level, day level, week level, whatever. You create a simple aggregating index, which defines the group by fields and the calculations on top of it. So whatever you want to do, like average, sum, min, max, whatever SQL functions you want to use. And Firebolt will maintain this rollup for you, this aggregating index, and serve data from there whenever your queries group by these fields. So what's very nice about this type of index is you don't need to change any of your select queries for this to work. Firebolt is smart enough to use the index if it can, and it will maintain the index for you automatically. So whenever new data is flowing into your base tables, all of the aggregating indexes on top of it will be automatically maintained, and you'll get the latest data in all of them. So these are the index types, right? Very powerful weapons to achieve sub-second performance, but also to be very cost effective, right? Because we are fast in executing the queries, we can do more in the same amount of time, right? So we are cost effective in that sense. One other thing before we jump into the Firebolt demo is our support for JSON, right? We understand that today a lot of data sets are not really, fully relational. We have data that's coming from applications, from different systems, and served in kind of array format or semi-structured format, JSON format, and so on. For this, we have a very kind of rich array of Lambda functions. And these are used within SQL. I'm going to show you an example. In a very efficient way, they're able to kind of crunch your arrays and your JSON data and get aggregations or get elements out of them. We use this in whenever we have JSON or kind of array-based data sets. And really, this is very, very efficient. And again, combined with the power of the indexes, a powerful weapon to deliver sub-second performance. All right, let's jump into a Firebolt demo. And for this demo, we're actually mimicking the SimilarWeb use case, right? So this is the Firebolt UI. My database is here. It's called search terms metrics. I have some of my scripts here on the left side. On the right side, you have the whole kind of data model, different objects, tables, external tables, views, and so on. And the middle part is actually my query editor. So what we're doing here is we're inspecting the schema, right? I ran a show tables here. We're focusing on two tables which are kind of interesting to us today. One of them is called domains. It's a dimension table, 5 columns, pretty small table, right? 10 million rows. Also, the size of it is quite small, compressed. It's only 181 megabytes. The other table is our domains metrics table. This actually holds the keyword data that you've seen in SimilarWeb's use case, right? So we have a mimic kind of sample data set where we are providing like 100 billion rows in 11 terabytes. So, quite a volume here, but you'll see how we perform in a second. So what we want to do is we want to export this data set. Let's just do a count here to see 100 billion rows. And we want to show you how Firebolt works with kind of progressing from simple queries to more complex ones on this scenario. One thing to notice here, I'm running a $4 per hour engine. So you can see the specs here. It's what we call a C8. You can see the the vCPU, the gigs of RAM that are available, the storage, and it's basically a one node engine. So $4 per hour, that's the total cost of my use case plus storage on S3. Very predictable, right? So, all right, let's take a look at our data set. So what we're doing here is we're running a lookup query to our 100 billion row table, right? We are filtering rows which have the visit date between November and beginning of December, and for specific domains, right? So we're focusing on Adidas, Nike, and New Balance, and we are getting the results set back. So if you remember our initial table, the search metrics table has 11 terabytes of data, right? What's interesting here is that we're scanning only 21 megabytes out of the full 11 terabyte data set. So you can see like the power of the indexes here. These are the sparse or primary indexes. If I do an explain and show you how this works under the hood, you're going to see that basically we are using the primary index in our explain view here, and we're using two columns which are part of the index, right? Visit date and domain, right? Both of them are part of the index, which means we're able to fetch them very efficiently from storage. So what happens if I increase this to like 2 months? Again, I'm only in 22 megabytes, really, millisecond performance. Let's do something more. Let's do a couple of months. So again, you can see how this scales nicely, right? It's very efficient. Because the data is indexed, we're able to fetch it and prune it very efficiently. All right, let's go into something more complex. So here in this query, we're doing a group by, so an aggregation. Again, we're hitting our 100 billion row table. We're grouping by the visit date, domain, and area code. This is almost like a country, right, from which the visitor is from. And then we're doing a couple of metrics. We're calculating the distinct search terms, average, search rank, and so on. So again, for 1 month of data, we have a couple of domains, and we're also filtering by different search terms, so NFL and shoes. And you'll notice that I have here a wildcard before the actual search keyword, meaning that for this particular column, I'm not using the index, right? The index is going to be based on this one. All right, let's run this. Again, you see like the performance and the actual scanned bytes, which is what we usually look at first, is really, really good, right? So we're only like at two megabytes of scanned data, and we are at 0.06 seconds, so quite nice for an aggregation, right? So if I do 2 months, again, you can see the scale and the speed. Let's do more. Again, we're quite nice here. One thing to notice is, even though we talked about our aggregating indexes, for this particular query, we're actually hitting the raw table. We don't have an aggregating index in this use case. Because the performance is quite nice even without it, we actually don't need it to power this query. If we see later on the degradation with data volumes rising or more complex queries, more complex aggregations, etc., then we can easily introduce an aggregating index, and we can create one even if we have data already populated in our base table. Right? I can create an index. It's going to be generating for a few minutes or tens of minutes, depending on the data volume, and then once it's generated, the queries will get served from that very index. All right, let's progress even more. So here, what we're showing is a combination of aggregation and joins, right? So we have our search terms fact table. We have our domains dimension table. This is a small one, right? 10 million rows. And we're joining them on the domain keyword. Then we're filtering, again, 1 month of data for specific domains and for specific search terms. What we're introducing here is another column, right, which is the open page rank, which is coming from the dimension table. Again, if I run this, you can see now that we do have a bit more megabytes that are scanned because we're doing the join, but still the performance is quite nice. So even if I, let's say, change here and go into search term like NBA, or I go into multiple months of data, again, you can see even though the scanned bytes are now going up, I'm still serving this below half a second, right? So pretty nice. All right, let's progress one step further and show you the Lambda function. So if you remember, we talked about support for semi-structured data within Firebolt, specifically JSON type of structures where you have arrays embedded within JSON. And if you have to traverse those arrays or do some more complicated calculations with the elements, you run into troubles, right? I mean, it's not something that's efficiently done in databases. In Firebolt, we have a wide array of functions. We call them Lambda functions or Lambda queries, which we actually use within your SQL to operate on the arrays that you have in your data set. So in this example, you can see the array function here, or sorry, the Lambda function here. We're calculating the max hourly rank for the very same query we executed a moment ago. So we're basically going through the arrays. We're finding maximum values of those elements, comparing them, doing some sort of calculations here, and then returning the results, again, in an aggregated way. So if I run this, you see that since we're traversing these arrays, right, we have a bit more volume, but we're still very, very fast. It's very, very efficient. Again, this goes back to the usage of primary indexes or sparse indexes, where we prune only the data that we actually need, right, based on your filters. And from that moment on, it's like pure compute power and query execution that's powering all of this. So this was the demo I wanted to show you. I have another one where we're actually demoing the use of aggregating indexes. So I thought, since we have time, it might be interesting to see. So I'm switching over to another demo instance. And here we have a database with a few tables. And one of them is quite large. You can see like 57 billion rows, 2 terabytes of compressed size. And so we want to see how Firebolt performs on this type of very raw or very kind of granular data, and when it needs to do the aggregation on the fly, right? So what we're doing here with our query is we're going to this base table called lifetime value. We are joining this table with 2-dimension tables, and then we're grouping by several fields, right? Six fields to be precise. Apart from that, we're doing a lot of calculations in terms of calculating different clicks, impressions, install counts, and so on. And we want all of this, of course, to be very performant. Right now, the query has a filter around a month of data, so from kind of March to beginning of April. Let's see how we perform here. Again, our engine here is, we have 2 engines. One is $9 per hour, the other is $4 per hour. I'm going to show you both. So you see here that out of the kind of terabytes of data, here we're scanning 4 gigs, so quite efficient and very, very fast, right? Again, we're performing all of this on a pretty large data set in sub-second. So how do we do this? If I run and explain here, you're going to see that we're actually hitting an aggregating index. So what happens under the hood is we have an aggregating index that corresponds to the kind of signature of this query, right? It corresponds to the different group by fields and different calculations that are used. And of course, it's being built on top of the base table. So our query planner is smart enough to kind of reroute your query and not go to the base table, but instead serve data from the ag index. And if you see the definition of the aggregating index here, the DDL statement, you'll notice that basically it's kind of similar to the query that we're executing, right? So it needs to include all of the different fields that we're grouping by and different calculations. Even if it has more calculations that are needed and kind of more granular data, we can still reuse the index because it has data pre-populated, pre-computed, and it's more effective that way. So this is a demo of the aggregating indexes. And really, we see a lot of power in these once you go into more complex queries and large data sets. All right, going back to our presentation, I think we have only a few more slides, and then we can open up the Q&A. So as I've said, we've been quiet for a while, right? We haven't had these product showdowns in the last couple of months, I think 6 months or so. And we've been cooking really hard. The engineering has been working really, I think, like if you see our roadmap and the features that we have lined up and the things that we're releasing, it's really going to be a good year. So first off, and I think this is probably the #1 feature that we've been requested from our customers, are mutations. So support for updates and deletes, to be more precise. Up until now, in Firebolt, if you wanted to delete data, you would do it on a partition level. So you could partition your table according to a partition key, and then drop that partition when you need to kind of update or delete data. So you drop and then reload again, right? By introducing update and delete, we're basically going into kind of more granular abilities here. So you don't have to partition your table anymore. You can delete specific rows based on filters and so on, like you would do in any other database. So update and delete are available. The other thing that's also interesting is what we call engine-less administration or system engine. This is a feature that we're currently rolling out, and it allows you to manage Firebolt through an engine that's always available, right? Which you don't need to provision. System engine will be there, always running, always. You can connect to it. Again, it's going to have its own endpoint. So you can issue queries to it. And those queries are usually used for like engine management or database management, right? So if you want to do create an engine programmatically, up until now, you would need to have a Firebolt engine running to do that, right? With a system engine, or what we call like engine-less administration, you're able to use this built-in endpoint that's always available and do everything from there, right? Create engines, drop them, change their configuration, start them, stop them, and so on. So this is a nice feature for overall kind of orchestration and maintenance. The third, and I think this is really a large one, which is being rolled out at the moment, are scalable joins and aggregations. So this is kind of a rebuild of our distributed query execution. And we've been testing this kind of live with large data sets. It's amazing to see, right? So With this new type of query execution, we're able to use the compute power even more efficiently than up until now. Meaning we're able to work on more granular data sets, on more complicated group bys, joins, aggregations, and do this more cost efficiently, right? We're able to utilize the engine's compute power, RAM, more efficiently, and also scale out and support data growth more efficiently. So this is something that I think if you have complex joins or complex aggregations over massive data sets, or you're doing something like ELT within Firebolt, this is something that's gonna make you very happy. And then finally, we have lots of stuff coming out soon in this year. I think for one of the kind of, at least from my perspective, the nicer ones or the cooler ones are, of course, ACID for DDL and DML operations, meaning you're going to have atomicity in your operations. Another one, which is very good, is Git integration. We're going to do integration from the Firebolt UI with the Git repo. So you can do script management through Firebolt and basically have your own kind of workflow from a developer perspective, fully automated for Git. And then we're also introducing new index types, kind of going again into more cost efficiency, and again focusing on like having as much as we can maintain and manage these type of indexes and new features for you, so you can just focus on like delivering use cases on scale and performance. So I think that's really exciting what's coming up. In terms of the ecosystem, we've been also very busy. So we do support a lot of tools and services today, right? If we take a look like from the left side here, data integration and ETL tools, which integrate with Firebolt, you're going to notice some nice names here. From orchestration perspective as well, dbt has support for Firebolt. We also use it internally within our BI team. And then if we go into kind of more BI and embedded analytics, you see a lot of different vendors supporting Firebolt. We do have our SDKs, so Python, Node, .NET, Go. We have really a nice support there. And of course, tools for reverse ETL or data observability, they also plug into Firebolt. So overall, like on the ecosystem side, integration side, we are starting to see good traction and growth. And of course, this, whenever you have tools that you already know and use, it's much easier to integrate with Firebolt that way. So it's a great add-on. Right, so from the content side, that would be it. Just before we jump into the Q&A, I'd like to invite you into this 2020 challenge, or the Data Warehouse Challenge. If any of this has made you, want to look us up, if you're interested, we're offering this nice challenge for you. So we're going to make your queries run 20% cheaper and 20% faster. And if we don't, then you'll get a pair of AirPods. So it's kind of a win-win, right? So if you're up for the challenge, I think Tamar will put the link into the chat, and hopefully you'll see Firebolt in action, and you'll see the performance that you can get out of your queries. Awesome. So questions.
Thank you so much, Luka. We have a bunch of questions also that people have been asking during the showdown, not only before the showdown. Alex is here, our developer advocate, trying to answer as much as he can. So let's try to answer some questions live, also the ones asked in advance. So let's just pick one. Which sources of data can Firebolt use as an input? Is it possible to pull data from AWS S3? And also, can Firebolt connect to AWS Redshift or Snowflake?
Okay, so our data source, let's go back to this slide, is today it's S3. So we integrate with S3. This is our we call this external table or external data. S3 is where you would have your data before it's being ingested into Firebolt. So at the moment, this is the only data source we support. We do have others rolled, up in our roadmap. But today, if you want to have data ingested into Firebolt, first you drop it to S3, you create an external table within Firebolt, and this is the kind of the interface how you get data in.
Cool.
Regarding Redshift, Yeah, regarding Redshift and
Sorry.
others, we don't have direct integration. For those, if you want to get data out of them into Firebolt, look up one of the tools that I've shown in the integration slide. Again, the process would be extract into S3 and then go from there into Firebolt.
Next question. What's the ballpark when Firebolt has the advantage? For example, from Snowflake, a ballpark for any clustering optimization is everything under a terabyte can be left to default. What's the ballpark size and query speed requirement when I should start looking at Firebolt?
I'd say start immediately. I mean, we really have like customers as big as SimilarWeb, right? But also much smaller. Customers who want to focus on speed and performance, right, of their use cases, and also deliver those use cases in a cost-efficient way. So I don't think there's like a threshold. Really, you should give it a go, and you'll see the power of Firebolt and this kind of efficiency of our indexes.
Cool. Next question. I'm really curious what you're doing with source data. Are you moving it somewhere else, indexing it in place? What sources can you read?
Mm-hmm. Okay, yeah, good question. I mean, we did touch on this a bit. Again, source of the data is S3. What we do when we ingest data into Firebolt, it goes through what we call a general purpose or read-write engine, right? So we get data in, and during this process, we're reading from your data lake and kind of transforming the original data, be it in Parquet, JSON, whatever format, into this triple F or F3 format. What happens here is we sort the data according to the primary index definition, we compress it, and we basically index it. So we're keeping track of the ranges of data. So we're very efficient at finding it afterwards.
What is the pricing model?
The pricing model, that's a good one. So there's two components to our pricing. One is storage. So that's basically a pass-through of AWS cost. So the same cost you'd get from AWS, this is the storage cost of S3. And then we have the compute cost, right? And the compute cost will depend on the engine size. So the actual engine that you select and the scale of that engine, the number of nodes, but it's fixed for the amount of time the engine is running, right? So we're only charging for the uptime of the engine. If it's running for an hour, the $4 engine, let's go there. This engine that I used in the demo, this $4 engine is going to cost you $4 an hour, regardless of how much you beat it, right? If you run one query or 1,000 queries, the price is flat per hour. So if you run it for half an hour, it's going to be $2, right? That's the simple mathematics behind it.
Can you elaborate on use cases like an API that's created on the back of Firebolt?
Okay, interesting. So definitely, this is something Firebolt can power. I mean, it's almost like a data app, right? Without a front end. So you can hook up your API, which you're exposing to your consumers, and have it run queries on Firebolt. As long as those queries are kind of, the query patterns are predictable in terms of you can control the usage of indexes, like here, right? You can target a column and make sure that it's using the index so we can prune efficiently. I don't see a problem. And of course, it's actually a very good and viable solution. So running REST APIs, custom REST APIs on top of Firebolt is definitely a good use case.
So we're already 5 minutes over time, and there are many questions also here in the chat and in advance. So we'll stop here. If we didn't ask your question, we're going to try to reach out to you. But anyways, you can schedule time to talk to us on our website, reach out. If you don't want to schedule time to call, just email hello@firebolt.io. or try the 2020 challenge. You have the link. So sorry we couldn't get to anyone. Just reach out to us. We'll answer any question. We'd love to talk. And thank you so much, everyone, for joining. Thank you so much, Luka.
Thank you, everyone. Talk soon.
See you soon. Bye.
Bye-bye.